Welcome to episode 5 of Applied Rationality. Here we're going to be talking about proving causation. And the reason why I want to talk about that in this episode is, well, I did want to talk about it at some point, but I feel somewhat compelled to talk about it right now because of where the last video left off, talking about this study by Hill and Dahl to prove that smoking causes lung cancer. Now, with full disclosure, I left that episode asking you as an exercise to identify what about the study would allow them to infer causation rather than mere correlation. And I assumed at the time, because I didn't look at the details, that the answer was the randomness. I assumed that they had conducted a randomized control trial. I'll define what that means in a minute. But in fact, it turns out that when I look into the details of exactly how the study was conducted, it was not a randomized control trial, and yet they were still able to infer that smoking causes cancer. And so what I want to address in this video is, in general, how do you prove causation, right? So that I can, in particular, talk about how they did in that particular study. But you know what? It's a worthwhile topic, so let's just devote a whole episode to how do you prove causation. In intro statistics, often we learn that correlation is not the same thing as causation. You hear this as like a mantra throughout the internet, and that's, maybe for good. But what you often don't hear about is, well, how do you prove causation? Now, one thing to address right away is that I'm using the word prove, and I don't mean literally prove. As we talked about in a previous video, in the sciences and in statistics, we very rarely prove anything. So when I say prove, I don't mean prove in the sense of there's a 0% chance that it's wrong or something like that. Rather, I'm just using the word prove as a shorthand for saying that if you take the data and interpret it in any alternative way, right? So if you have an alternative theory that explains the data, it is so statistically improbable that no reasonable person would interpret the data that way. That's what I mean when I say that we are proving something statistically with data. Now, let's talk about a randomized control trial, often referred to as an RCT for short. And what you do in a randomized control trial is you have some group of people that you're trying to study. Let's say that, for example, you're trying to administer a drug and to learn whether or not the drug cures a disease, right? There could be a lot of other things that you would use a randomized control trial for. But that's a fairly easy one to understand, so let's go with that. It's fairly common, too. So the idea is you want to take a pool of people randomly selected so that there's no bias or anything like that, and then you want to, within the group of people that you selected, randomly assign some of them to just keep on going as normal. Sometimes you also you give them a placebo or something. We might talk about that in a future episode. But just imagine that some of the randomly chosen subset of the people that you're studying, they're the control group, meaning that we simply do not do anything to them. They don't get treatment, whereas the other randomly chosen people in your group are assigned to get the drug, right? And so then you've got the control group, you've got the treatment group, and then we're going to study what happens to them. Does their disease get cured or whatever? Or is there some, whatever you're trying to study? Is there lower cholesterol or whatever the case might be for what you're trying to study? And then what you do is, with these people, you conduct the study, you gather the data, and you look for a correlation. Now, I claim in the context of a randomized control trial, when you get a correlation, it must mean that there is a causal relationship. And in fact, right, whatever the treatment is must cause whatever the observed outcome is. And so why is that? Why is it that in general, when you're out in the wild not doing a randomized control trial and you observe a correlation, you are not able to infer causation? But in the context of a randomized control trial, as I have described it here, when you observe a correlation, you are able to infer causation. Well, let's consider two scenarios and see, what happens, basically. So suppose that smoking does cause cancer. If smoking really does cause cancer, and we perform this whole experiment, well, because smoke, right, the people who smoke are going to have a higher rate of cancer because we're assuming that the causal relationship exists. And then we'll see the correlation, right? So, okay, so if causation, then we see the correlation. In fact, that's always true, whether you're in RCT or not. Okay, let's now think about the other scenario in which no causal relationship exists. I claim that in that scenario, in an RCT, you must not see a correlation. And why is that? Well, it's because the people were assigned to control and treatment perfectly at random, and so whatever you observe as the result should be just exactly the same, rates and, so on, as if there was no treatment whatsoever. So, so effectively, if there is no let's put it the other way around. If the treatment does not cause the outcome, then you should not see a correlation because of the randomness in the initial phase of the design of the study. So anyway, what this then means is that we have an experimental design that can detect causation. Now, next, let's make sure that we're really clear about why that doesn't work in observational studies, right? Situations where we do not have a randomized control trial. And I want to make sure that we're clear about this because especially in the smoking situation and in lots of others, we cannot do an RCT. Why can we not do an RCT? Well, if you think about what you would have to do, you would have to make you'd take like a population of people, presumably non-smokers, because we want to imagine giving them the, so to speak, treatment of, smoking. So you'd have to take a bunch of non-smokers, make some of them keep non-smoking, that's probably fine, but then make some of them go start smoking. And then, if there really is a causal relationship, we basically just made a bunch of people start smoking, and then they're going to contract cancer at a higher rate, and some of them will die, and that's just horribly, horribly unethical. So we cannot conduct that study. So if conducting an RCT sort of study is impossible, then does that mean we've reached a dead end, that we cannot study whether or not smoking causes cancer? Well, no, not at all. That's why I want to talk about this. We're going to look at, why is it that these kinds of observational studies that are not RCTs, what can go wrong? And then we'll start talking about how we can address what can go wrong. To do that, it's always helpful to have examples. So let's kind of keep in mind some 4 relatively easy to think about examples. So the first example is going to be the one we've been talking about this whole time, and we're going to be talking about X correlates with Y, right? So imagine that smoking correlates with cancer. That shouldn't be hard to imagine because it does. But in any case, now let's next imagine that the temperature on any given day somehow correlates with the stock market prices on that day. It's a bit of a funny one. We'll think about what could be going on there. The next example, suppose that we notice that cholera outbreaks seem to correlate with a region's exposure to unsanitary water. And then the last example will be that drowning incidents correlate with ice cream sales. So what could explain some of these correlations? Well, one explanation that you always kind of have to worry about is mere random chance. And in fact, this is what's going on if we were to see a correlation between temperature and the stock market. Almost certainly there is no causal relationship one way or the other. Temperature does not cause the stock market price to go one way or the other. I mean, you might have some theory, but if you observe this correlation, you probably just need, maybe on 3 days, right? You'd be right to observe a correlation like this. You're probably doing a small sample of days, like hot day, high price, cold day, low price. And and you just need to wait a few days, collect a little bit more data, and then you'll start seeing the trend not being observed again, right? So when it's mere chance, often you can just collect a sample size large enough and make the probability of that mere chance go way down. That could be the explanation for what's going on when we talk about the correlation between smoking and lung cancer, but given that our sample sizes are so very, very large, this is extremely unlikely. But it's always worth noting that you could observe a correlation between X and Y merely by chance. You can't completely rule that out, although we have good methods, namely just a large sample size, to push the probability of that problem way down. The next explanation is perhaps the easiest one to understand. It's exactly the whole point of this whole conversation, which is that X causes Y, and that is almost certainly what's going on in the smoking causes lung cancer example. But let's notice that if you notice that X correlates with Y, it might be because the causation goes in the other direction. This is relatively easy to see in the example that I gave about cholera. Remember, we said that X was contracting cholera and Y is exposure to contaminated water. Does cholera cause you to go get in contact with contaminated water? Almost certainly it does not. But the correlation was observed, and we now know with very good science that exposure to contaminated water causes one to contract cholera. So if we applied this idea to the smoking scenario, then we might worry that possibly cancer causes smoking. Now, this might be a little bit of a stretch, but, even if we feel like the idea is kind of silly, we typically, as researchers and rigorous, rational people, want data to more directly address the issue rather than just saying, well, that just seems silly to me. And here's, a half plausible story about what could be going on there. Maybe cancer causes smoking because, let's just try to think of how that could possibly happen. Maybe there's the cancer in your lungs irritates your lungs in some way, and somehow underneath your sort of like conscious decision making inclines you towards smoking cigarettes, for instance, right? So maybe it's a silly idea, but we'd want to rule it out with real data. So anyway, the point here is that when you observe a correlation, well, yes, maybe X causes Y, but another possibility is that Y might cause X. But often a more serious concern is that there might be some third lurking variable Z. And this is something that's nicely illustrated in the example that I gave, where X is drowning deaths and Y is ice cream sales. Now, if you see that these two are correlated, are you going to explain that by saying that drowning deaths cause ice cream sales? It's really hard to imagine, some grieving mother, soothing her grief with just buying some ice cream or something like that. That can't be what explains this data. Would it be that ice cream sales cause people to drown? Well, there's some folk theories about eating before swimming, but I think we can pretty easily rule that out. No, if you see this correlation, almost certainly the explanation is that there is a third lurking variable Z, which is namely the temperature on any given day. If the temperature is very high, then that's going to cause a bunch of people to go drowning or to go swimming. And then because there are so many more people swimming, then just like by the high rate, then you're going to get a higher rate of percentage of them drowning. So anyway, and then the hot days are also going to cause people to buy ice cream, for instance, right? So this would be a case where you'll see a correlation between some two variables X and Y, but the real explanation is a third yet unidentified variable Z, which in this example is the temperature on any given day. Now, how would that apply to our smoking causes cancer example? Well, maybe there is some third variable and a relatively, not perfectly, but relatively plausible third variable there would be genetics, right? Maybe you were just born with genes. There's some gene switch in you that causes you to smoke because of just some poorly understood, especially in 1950s where they knew very little about genes, some kind of gene that would incline you towards smoking and also eventually cause you to develop cancer. Now, I will say that people at the time did worry about this. There is a statistician, Fisher, who I believe defended precisely that idea. A few other people followed him. It's worth knowing that he was in fact funded by the tobacco tobacco industry. Now, that's not necessarily to say that he only did and said these things because of his funding from the tobacco industry, but perhaps he was more recognized, he had more resources to publish and get attention than he otherwise would have if he had not been funded in this way. But in any case, whether he was funded by the tobacco industry or not, that is not, right, that's mere suspicion. It's worth thinking about, and you always want to have, no conflicts of interest, right? So that certainly sounds like a conflict of interest, and so that's not a good thing. And it's worth noting that, but as far as having rigorous statistical arguments are concerned, that does not really matter for whether or not the hypothesis is true. So anyway, there you go. Those are the main ways in which, if you observe a correlation between some variables x and y, but it's not done in the context of a randomized control trial, then you might still see a correlation even when causation does not go from x causes y. So again, if we cannot, right, if there are all of these problems with observational studies, and in the case of smoking and cancer, the only thing that we can do is an observational study, then does that mean that we have been lied to by the medical, right? Is that all we can do? Have we been lied to about having proved that smoking causes cancer? Well, no and no. Right, that is not all we can do, and that is not all that has been done. We have not been lied to. The medical community, well, there are some other arguments that are actually relevant to the Hill and Dahl study, and also there have been subsequent studies that I'll describe in a few minutes that actually kind of sort of seal the deal. Now, one relatively straightforward way of dealing with one of the issues is to deal with the problem about there being these lurking variables z, and you can try to minimize that problem by thinking of every possible variable z that you can come up with, and then testing it for a correlation, because if there's no correlation, then there cannot be causation, right? You don't need an RCT for that direction of the inference. So you think of every possible z, and this is in fact what Hill and Dahl did, is they, in their questionnaires for all the people who were studied at that hospital, they didn't just talk about smoking and cancer, they tried to just list everything, whether it seemed plausible for it to have something to do with cancer or not. They asked anyway, looked at every possible thing from work habits to other lifestyle choices, exercise, or who knows what. Right? Like they tried to just account for everything that they could possibly account for, and in so doing, they eliminated a lot of possible lurking variables z. Because all of them demonstrated no correlation or extremely weak correlations. So that's one way that you can demonstrate, or you can eliminate one of the problems, at least somewhat weakly. I mean, you're always at threat of being like, well, did I really eliminate everything? Is there possibly some other variable that we just didn't think of? And yet it's actually the thing that's responsible for the correlations that we observe. That's always possible, but you can really sort of push down your concern, right? You can make that less and less likely by sort of exhausting more and more possible lurking variables. But here's another way that you can demonstrate, or at least make more likely, that X causes Y, and that is for there to be a time relationship, which is exactly what was true in the smoking and cancer study, is that smoking seems to always precede cancer. So there's this time element that kind of eliminates the possibility that Y causes X. It doesn't do so perfectly, because you could, again, come up with some of these relatively hard to believe but not perfectly ruled out scenarios, like maybe when you have lung cancer, it actually starts much earlier than we're even able to detect. It's somewhere deep in your lung cells or something like that. It causes, I'm just going to make up a complete fantasy scenario just to be like, this is something that the statistics alone couldn't rule out. You'd have to do more investigations, which we did, and we know that It doesn't work this way. But anyway, let me just say this, silly idea that for at the time, for all we knew, this is what was going on. Inside of your lung cells, they develop cancer first. It causes some kind of irritation, and that sort of inclines you towards increased smoking. So then maybe it really is that the cancer causes the smoking. It's implausible. We have no evidence for it. Later on, we found that mechanism simply isn't there. Anyway, the point is that time, right? If you can establish the sort of temporal order of things, and here it seems like we've got a pretty good idea that the temporal order is that smoking comes before cancer, and so it wouldn't be that Y causes X, right? So if there is causation, it would have to be X causes Y. Somewhat similarly, you can also talk about a mechanism, right? So if we, let's think about, well, actually a nice example, I suppose, is the cholera example, because we actually do know mechanism, especially, and this was an important part of the history of the development of science, was the invention of the germ theory of disease, and it really got one of its biggest sort of confirmations in its ability to identify the cause of cholera, right? There was an observed correlation between places where people lived and the contracting of cholera, and it was found that certain little microscopic bugs that they were just then discovering were in the water in the places where people were contracting cholera. And there we have a mechanism, because we've got these little bugs, and we can imagine you drink in the little bugs and they get into your gut, and somehow they inside of your body wreak all kind of damage. And so there's a mechanism, and when you have a mechanism, right, that is much stronger than having mere statistical correlation, it really sort of makes a strong case that the correlation is caused by this mechanism. Also, another great virtue of having a mechanism, a proposed mechanism that explains the correlation, is that once you have the mechanism, you can go test the mechanism. So for instance, in the smoking and cancer situation, we could say that maybe, and I think we now know this, I'm no biologist or doctor, so I don't really know the exact mechanisms going on here, but I believe the idea is that when you inhale the smoke, it comes into contact with the cells, it damages either the DNA or the RNA or something in the cell, and the cell starts producing the cancer. That's the mechanism. Well, when you have a mechanism, you can now somehow, I don't know exactly how they do this, but it gives you something to go now, like, actually look for the mechanism, see if you can't directly observe it. And as soon as you do that, right, if you can directly observe the mechanism, now you know sort of proof positive that you know what the causation is. Now, while Hill and Dahl did point out at the time that smoking seems to come before the onset of cancer, and so they had that part of the argument in their hands, not enough was known about biology and especially about DNA and the workings of the cell. So they couldn't have possibly supplied a mechanism at the time, although I believe later studies have demonstrated that this mechanism is correct for smoking causing cancer. Now, there are many, many ways to demonstrate causation even outside the context of an RCT, but this is the last one that I'm going to talk about. I'm trying to talk about the ones that are kind of the most convincing and the kind of biggest stars of this world, so that we keep things a little bit limited for time and complexity here. But so the last one that I'm going to talk about in this video is the idea of a natural experiment. And so let's start again from an example. In 1980, Mount St. Helens erupted. Now, researchers at the time had already been monitoring the chemical composition of the soil in the area around it. And after the eruption, of course, there's going to be a bunch of ash and lava, and where they went to some soil areas rather than others was mostly guided by random factors like wind and topography. And so this effectively got you an RCT without trying to design or build it. You could see what the volcano eruption caused in the change in the soil composition. And so a thing like that is called a natural experiment, and so you could say that some natural experiments occurred in the case of smoking and cancer. Now, this had to happen after the Hill and Dahl study came out. People became relatively convinced that smoking causes cancer. In the wake of that, some countries outlawed smoking, others did not. And, that kind of gets you a natural experiment where we look at the countries that banned smoking, and we'd also have to look at how effectively they banned it. But we can then observe the corresponding outcome of whether or not cancer rates decreased or whatever, and we see that they do. So that seems like we've got a relatively good natural experiment. It's not as good as an RCT because you always have to worry, well, maybe the countries that banned smoking were already experiencing higher rates of cancer, and then that put them into a panic, and then they, outlawed smoking or something. Again, right, like so the, maybe it's not quite as good as an RCT because you're not perfectly controlling. You're not perfectly using randomness because any of these natural, or so to speak, natural mechanisms that assign treatment and control, they're often not as random as we would really want them to be. But it's still, right, I mean, to imagine that that's the full explanation of the data is really hard to believe. So that's pretty good, even if it's not as perfect as an RCT. But there you have it. So if I now have to actually finally answer what was it about the Hill and Dahl study which allowed them to infer causation, well, it was correlation. But on top of that, they also needed to have things like the temporal ordering and the fact that they eliminated a bunch of other variables, right, these lurking variables z, by asking all of these other questions as well.